many of you have heard that this is a program that we developed almost 2 years ago for full professors to talk about their experiences as a faculty member and share it with their colleagues, students, staff, etc., and have a chance to actually have a discussion with the head and the dean about the prospect for the next 7 years. So 7 is one of the key things. But what we usually don't talk about is how this program was developed. And Kathleen, today's speaker, was actually one of the key individuals who actually designed and put together the entire program. And to a large extent, we're implementing it exactly the way it was proposed. And so I believe it's a real special honor to have her be part of this series and share with us her experiences. And I'm very pleased to let you know that she actually got her PhD at Stanford and joined Purdue in 1982. So she's been here for a long time, and she is the Sue Low Distinguished Professor of Aeronautical and Astronautical Engineering, an honor which she received back in 2004. And so I'm very happy to let her tell us her perspectives. Thanks, Kathleen.
So as Claude said, this series was conceived about 2 years ago. We ran a pilot program last year, and this is sort of the implementation. Now, part of the goals of this is to have an opportunity to share what we do with our colleagues. But the other part of the goal is to look back over our career and sort of assess how we got here and what we've accomplished along the way. Now, in looking back, like a lot of folks in my generation, I realized that my career actually has played out against a backdrop of technological change as well as social change. And those things have influenced both some of the options that I had along the way and some of the choices that I made. So that's all been sort of an interesting look for myself in looking back over what has occurred. Nevertheless, anybody who knows me actually knows that I am all about orbital mechanics and celestial mechanics and orbital dynamics, actually. But not just from a mathematical perspective. I'm also really interested in vehicles and how they move throughout the solar system. I admit that at various times I've actually also looked at star systems, but for the most part I've been focused on spacecraft and vehicles. Now, collaborations have also been key throughout my career, and this particular graphic that you see on the screen here actually was one of my colleagues put this together about 15 years ago, Martin Lowe from JPL. He's actually a mathematician, but at that time it was our view, our collaborative view of what pathways through the solar system could look like. So in going back, what I wanted to address, I guess, is how I got there. How I got to this particular point. Now, I actually started my path to Purdue, so to speak. I actually started at Iowa State. Where's Tom? Okay. And I actually lived in Town Hall when I was an undergraduate there. I didn't live there, but that was where aerospace engineering was. Long moved before Tom Shee arrived there. But one of the interesting things about it was, as an undergraduate, everyone in the department, all the students were required to take orbital mechanics. And when I was there, it was taught by John Tannehill, who was actually in CFD out of the aerodynamics group. Now that's significant, and I'm going to come back to that a little bit later. Nevertheless, he taught me what I knew about orbital mechanics at that time, and I really liked it. But he taught out of a book by an astronomer that's also significant with this story. It's also interesting to note that at that time, it was a long time ago, but at that time in the department, when I went through, there were only 2 women in our class, myself and one other. And so that was also something that would later influence what I chose to do. But I did graduate. I did get my bachelor's degree in dynamics and controls, and I did try to move on. Now, at that time, what I thought I wanted to do was go into the aerospace industry. Again, it was a while ago. Things were different. The aerospace industry wasn't exactly, though, at the forefront of social change. And they weren't really interested in hiring women. Now, they told me that at the time. There may have also been other reasons that I wasn't a good fit for them. But I had to think about then how I was going to accomplish my goals. If I had been hired by the aerospace industry at that time, I may still be there. But I wasn't, and actually I went to a dinner with a friend who was interviewing with Procter & Gamble, and it turned out Procter & Gamble was really interested in hiring me. So I decided, wow, this would be like really different. So I went, and the first thing I did with my bachelor's degree in aerospace engineering was I went into work for P&G, and I went into line management. Went to the Kansas City manufacturing plant because, as it turned out, P&G was looking to, at least at this plant and at least for the two individuals that I would work for there, they were interested in pushing those social boundaries. They had one woman in the Kansas City plant at that time. She was a process engineer, a chemical engineer, but she was part of the staff. So they said, let's put you in line management. And there were two of us hired. I went into liquids production, and the other woman went into solids. So I was a floor supervisor in liquids packaging. Now, that was the first one they had had. I was not a popular choice in the manufacturing plant. Nevertheless, where I worked looks kind of like this lower right graphic here. That is a production line. Looked very similar to that. To survive, I learned pretty much how to take apart and reassemble nearly every piece of equipment in that room. Learned a lot. I also, in my aerospace engineering background, really hadn't been very, trained in personnel issues. So I learned a lot from that experience too. You never succeed alone, however. And in looking back, I realized that my immediate supervisor, as well as the division chief who was interested in this grand experiment, really supported me a lot. And I bumbled along, and geez, look what happened, I got promoted. So the next thing I knew, I was a department manager. 2 years after my bachelor's degree, and I was the department manager for the production of liquid product. So I made Joy, Ivory, and Dawn, if you guys have ever done that in the Kansas City plant, that was what I did. The people who worked for me were all men, and the youngest one was 20 years my senior. So that brought other new challenges. But I learned a lot. I would have been helped a lot if I had a chemical engineering degree. It would have been helpful, but nevertheless, I persevered. I was way out of my comfort zone. Nevertheless, the company was satisfied, but I really, really wanted to return to Aero. So I told them that I wanted to leave, and I figured my path forward would be to go to graduate school. So I decided that that's what I wanted to do. I was accepted at Stanford. I told them that that's what I wanted to do, and their response was, oh, you just want to move to San Francisco. We'll transfer you to the Folger coffee company, the plant out there. So I said, I don't even like coffee. So I left and gave up my full-time position for the life of a graduate student. So I ended up at Stanford in the Aeronautics and Astronautics program. From manufacturing plant to the Stanford campus was a nice change. This is the Duran building, which was the building that housed aeronautics and astronautics, so that's where I went. These two folks were on my committee. They greatly influenced what I did. Dan DeBray was in dynamics and controls. Art Bryson did controls and estimation. Both of them helped me significantly. Like I said, I don't think I would have made it without the support of various people there. I was told that at the time that when I did get my PhD, I was the first woman who would get it in D&C from this particular department. But rather than that, what I remember is this Duran building, because the aerodynamics graduate students got all their offices up there on the top floor, where there was this beautiful outdoor patio. This great, all that you can imagine about just wandering around the plants and all that. The D&C graduate students were in the basement. Okay, we didn't even have any windows. but we thought of ourselves as more resilient, we were the hardy bunch. And I eventually did, settle in there and so on. My actual advisor was John Breakwell. Now, he was a mathematician from Harvard and Oxford. He, though, had worked for North American Aviation and Lockheed before he got to Stanford. So he was connected in the field. He was, really an interesting guy. He was quite rigorous, but he was also, fun, and as you can tell from the graphic, kind of quirky. But that actually helped us a lot in how he looked at things. I would also say that he was, at that time, the one who introduced me to the international community. He got me involved in the International Astronautical Federation, of which I participate to this day. I participate in a lot of societies, but this one has been particularly a source of a lot of ideas and collaborators over the years. So that I also thank him for. He also did something else. He sent me off to JPL about as often as he could, I guess. And I worked there working on comet missions, actually. And on the left there is Temple 1. That's a comet that was visited in 2005, so we actually know what it looks like. But I was actually working on Temple 2. We were trying to put together a mission to Temple 2, and this was important for what I was eventually going to be working on, because trying to do a mission to Temple 2, we were working on what do we do when we get there. And so one of the questions was, and this to my graduate students and some of Professor Longusky's, this will seem funny, but at the time, the core question was, can you orbit a comet? Okay, and now we do that all the time, you think Rosetta and stuff, but at the time, that was a key question. And we were trying to figure out, because that would determine how the mission would be run. So I was finally back to my orbital mechanics roots, trying to answer fundamental questions about what we could do when we're in this vicinity. My own students, of course, will recognize here the figure on the right, because that was some of the analysis, the zero velocity curves, were some of the analysis that we would use to try to figure out, could you do this? And so out of that work, I got my very first conference paper that I went and delivered, and so, big excitement. Looking back, it wasn't very well written, but, we did it, and it was very interesting stuff. So I did go back to Stanford then and graduate. On the left are some of the trajectories that I looked at the time and produced. On the right is the modern visual of those same trajectories produced by some of my graduate students. Looks a lot better, but the calculations were much the same, and I actually did get my PhD. Now, it is interesting that they had a PhD in aero and astro engineering, and they also had one in aero and astro sciences. And I ended up with my degree in the sciences probably because my advisor was a mathematician. But I did that, and then I came to decide now I can interview, years have passed, I can interview at academic institutions, I can interview in aerospace companies. They were interested by then. So I had a lot of choices. I ended up coming to visit Purdue. These are some of the people I met on my interview day. Henry Yang was the head. Some of you know him, I think. He was the head. He recruited me. We lived in Grissom Hall then. Everybody remembers that, or if you don't remember it, it's okay. My deal with Henry, though, was that I would come as a visiting assistant professor because I had no intention of staying. But I came on my interview. I met Violet Haas and Leah Jameson. Henry sent me to meet them. They constituted the entire women faculty in engineering. Okay, that was it. So we all got together. But they convinced me that this was a good trek to try and make. I also put up there the picture of Jack Bogdanoff, who probably only maybe a couple of you know him, but he was a faculty member here at the time. And he was for those of you who are in aero, he was the professor who taught 340. Okay. If I came, I would be the eventual person in 340. And Jack was not at all sure this was a good idea. So I came on my interview, I went to his office to interview, and he put me up at the board and was giving me a test to see how I was gonna do. We argued a little about angular momentum, and in the end, I guess it was okay because I got offered the job. But he was always interesting, and I guess today I look back, and maybe that was one of the factors that convinced me that maybe this would be okay if I stayed here. So I also knew, and maybe even in Aero people here don't know, that another person, though, that was at Purdue at the time was Harry Pollard. And if you don't know him, that's because he was in the mathematics department. He was a mathematician, but he was here for almost 25 years. And just as I was coming, we were losing Harry. But he was very well known from the mathematical perspective for his work in celestial mechanics and the in-body problem. And in mathematics, actually, some of his students that he graduated then went off and had illustrious careers in mathematics in this field. So that was also an attractive potential collaborator for me at the time, but unfortunately I was here only a short time, and he passed away. However, how did I go from there to what I work on today? So I want to talk a little bit about the field. Celestial mechanics is a very old science. It talks about the motions of celestial bodies, and it was fundamentally founded by Newton. So it's been around for a long time. The questions associated with it are very ancient, but is recognized as a discipline, sort of starting with Newton, so it's been around for a few hundred years. Now, as evidenced by Pollard, celestial mechanics actually has its roots in mathematics and astronomy, and it was taught in the math department. It was taught in the math department here, and up until the second half of this century, teaching it in engineering, you didn't look really at celestial mechanics. So that was notable. In looking back at celestial mechanics, though, the motion of celestial bodies, I would also want to point out that it is not limited to just gravity. It's not only gravitational forces that influence the motion of bodies. So when I talk about celestial mechanics, we also include some of those other forces. Now, it's also true today, in 2015, that celestial mechanics and chaos are always linked. We hardly mention celestial mechanics anymore without including that fact, and that's been influential in what I do. But before I go back to that, what is the difference between celestial mechanics and astrodynamics, which is what we're talking about when we talk about engineering? Astrodynamics takes the science of celestial mechanics and is really focused on the motion of natural and man-made objects. But when we use it to support missions and vehicles, man-made vehicles, we're talking about more than just the trajectory. So astrodynamics actually incorporates all the aspects that we need for space flight. They are not independent, all of these different things on the list. So they all are interactive. And so anybody who is a practitioner of astrodynamics actually has to know something about all of these, because they're all going to interact. For the purposes of this discussion, I'm going to focus just on the orbits and the trajectories. But remember that word chaos, which means that we really can't separate all these various things because they're all interdependent. But for the moment, just talking about the orbits. We start in celestial mechanics talking about the two-body problem. And so that's where its roots are. That's the legacy we have from Kepler and Newton. And it's probably what everybody saw in their high school physics class, I'm guessing. True? For the most part, we think about it in our applications to spacecraft as fundamental behaviors. It's where we get the ideas of putting together spacecraft trajectories when we're talking about ellipses, circular orbits. Down in the bottom there, that's a hyperbolic orbit, which we use for gravity assist and so on. So that's kind of where we started with all of this. Now, that legacy gives us a wide range of motions for spacecraft. And that's what has interested me for a long time. This is the kind of analysis that I did when I was an undergraduate. Fundamentally, for spacecraft, it originates when I'm looking at the gravitational influence of one, like a planet, on the motion of the vehicle. The vehicle is very small in mass, so for our discussion here, I can look at these kinds of motions, and that's what we're talking about. Now, I might point out that one of the problems with a graphic like this is that it looks simple. It is not, okay? And if you're actually going to do any of this, it is not simple at all. But these fundamental conic behaviors have formed the basis for a lot of what we've historically done in mission design. It's covered a wide range of scenarios, and we've done a lot of things with it. And we continue to do a lot of applications by taking the fundamental motions and pulling them together. The example I happen to have here is the trajectory for Cassini. So that happens to be one that is not at all trivial to accomplish. It wasn't trivial to design. It's certainly not operationally simple to do, but it involves putting those, in its most basic sense, putting some of those basic conic forms together. So there's some elliptical orbits here, there's gravity assists, which means there's some of the hyperbolic ones. And we get out to Saturn eventually. Cassini is still operating off there, but it took many, many years and was a non-trivial process. I couldn't help, thinking of Cassini, I couldn't help putting in here the fact that some of my students have, in fact, looked at that Cassini orbit. These are a couple of my former graduate students in the Envision Center, looking at all of the pieces that might need to make that up. This is also them over there. I do want to emphasize, again, it's challenging to do this. Over the years, we've done amazing things with just using those elements to get us started. And we will continue to do that. There's lots of things on the table that will actually be yet, I guess, a testimony to what we've been able to accomplish with this knowledge of motion through the solar system. On the other hand, for some types of problems, using these basic elements that we use in this trajectory and others, using those basic elements, that's the perfect approach, and that's exactly what we want to do. So using those conic elements to some degree is exactly the right thing. Certainly if we're close to a planet like Leo or the ISS, those are the elements that you want to use. But increasingly, there are new opportunities, and other types of fundamental behaviors may be the best choices. And that's because we now have other places to look for motion as we move through the solar system. So in this particular case, it takes ideas that originated about 100 years ago as a different way to look at that gravitational problem. And now we're starting to reap the benefits of sort of an expanded view of what we can do in the solar system. And that's actually what I was interested in and the direction that I took when I wanted to look at some other types of motions. Now, it started back about 100 years ago, and this is where that word chaos comes into the picture. So it's where we go back to the mathematical roots of celestial mechanics, and about 110 years ago or so, there was this huge shift in how we think about the gravitational problem. It was due to Poincaré, and it was a very different view of what we could accomplish. So Poincaré came around and did not solve the problem of what's today called the in-body problem, the same thing that Harry Pollard was working on. It had not been solved then, and it's not solved now. It's one of the biggest unsolved problems in mathematical physics. But the work that he did on it actually was the seed for a number of branches of mathematics. So it made a big difference in the problem. What does it mean as far as we are concerned has to do with this difference between starting with an orbit that is fundamentally influenced by one gravitational field and saying, well, what if I add another gravitational body? So what if instead of just the Earth, I also add the gravity of the moon simultaneously? This little guy here looks like a little bug, but actually that's the Artemis spacecraft. And the behavior of the vehicles can change significantly. And just adding one more body adds significant complexity in the problem. And one of the reasons for that is because in 1885, Poincaré recognized that the gravitational problem includes chaotic behaviors. So he recognized chaos. And that was the step that said the options in the solar system are much broader, and there's many more possibilities than was originally envisioned by Kepler and Newton. It is very computationally challenging, however, and in 1900, the tools did not exist, the computational capabilities didn't exist in order to exploit this discovery. On the other hand, it changed celestial mechanics forever, and since then, mathematicians and now engineers have been examining this problem to see what that opens up, to see what new possibilities might exist. Celestial mechanics actually has never actually been the same, and there's now new options that are coming forward. What does this actually mean when we're talking about a problem that we want to look at? So here here in the center is the Earth, and here is the moon. And right now, I'm just going to say that our view is one that maybe we're riding with the moon, or we're standing on this red line. Now, if I am interested in thinking about those two-body problems and thinking that the Earth is the only thing that influences me, I might be thinking that if I calculated an orbit in this neighborhood, I would get this nice ellipse, okay? And admittedly, that if I'm standing on the moon and this red line is moving because the moon moves around the Earth, I might actually see that thing change with time, and it may precess a little. But if I look at it, what I see is something ordered, predictable, something that I can actually grab hold of mathematically and I can work with. But in fact, when I add the gravity of the moon, when I go and I add the gravity of the moon, what Poincaré envisioned was that instead of seeing this, I may see this wonderful picture produced by, actually, I think it was Cody over there. But this is what I might get instead. That wasn't what I was envisioning, but this might be actually that chaotic response that I see. This is in the Earth-Moon system, and I can think of it two ways. I can think of it as, oh, this is bad, and I'm going to have to try to find some way to control this. Or I can think of it as an opportunity. I can think of it as, how can I use this to accomplish different things? And so clearly, the mathematicians and the early engineers were thinking that maybe we can leverage this type of behavior. So that's actually what we wanted to accomplish. But we had to figure out sort of how to harness all this. And that's where you start attacking a nonlinear problem by looking for the equilibrium points. So in this particular problem, any of you who work with either Professor Longuski or myself would recognize these as the equilibrium points in this problem that involves both the Earth and the moon. If you're not in D&C, you might even recognize these because these are the Lagrange points, which many people have heard of now. What they actually represent is the equilibrium. Essentially, they would be the locations in the Earth-Moon space where the gravity of the Earth, the gravity of the moon, plus the centrifugal force due to the motion of the moon around the Earth are all balanced. So there was a lot of attention early on, way back shortly after Poincare, in trying to see what this information could give us. So what could we learn if we can't solve the problem? And I don't want to end up there. What can I learn by looking at these equilibrium solutions? The other thing we remember is that the equilibrium solutions also exist if I recast the problem where the two gravitational bodies are the sun and the Earth. So in this particular case, the Earth is buried in those 2 points. I can't even see it, so I zoomed out. But in either one of these problems, understanding those equilibrium structures and what motion might be around them turns out to be important. If I go back here for a second in the Earth-Moon problem, one of the things that was learned early on is that you can move in the vicinity of one of these points. These points are empty points in space, but you can still put an orbit around them. So in that particular case, we wanted to use this information, and so particularly in the mathematical community, there was a lot of focus on these points. These points, you can predict where they are numerically. Outside of these two guys, which are 4 and 5, which are located at the vertices of an equilateral triangle with the Earth and the Moon, those equilateral points I can predict where they are and I can solve for it very easily. But these guys, I cannot. So they're solved, but I can solve for them numerically. So there's a lot of focus on learning something about that. There was also time spent on sort of understanding what the gravitational flow would be in this world where both gravity fields are important. And in this graphic, you see the Earth and you see the Moon. In this case, the sun is way off to the left there. For the moment, ignore it. And we're just looking at those lines, which are different energy surfaces associated with flow in this region. Same kind of thing would occur if we talked about the sun. There's the Earth over there, there's the Moon. These are also different energy levels in this space, but that would actually give you a lot of information about how new types of behaviors might be offered if we look more carefully at this environment. However, all of this is based on numerical work, and if I'm going to talk about numerical work and I'm going to talk about the nonlinear results of all this effort, we really have to move forward until we have the computational capabilities to calculate things like the orbits around these points in the nonlinear problem. This is a graphic that was produced much more recently, but it actually gives us some of that information about, in the Earth-Moon problem, the kinds of behavior that you can have include all of these types of orbits. Now, these are all orbits that are essentially, here's the Moon, the Earth is way over to the left, so these are all perfectly fine orbits. Some of you have asked me questions about halo orbits before, and this is what they look like. And these are possibilities that existed that are due to these the extra gravity field and the rotation of the Moon around the Earth. And they offer a sort of different option for mission scenarios. I would also note that this surface represents the collection of all these different orbits. They're three-dimensional, and each one is represented by a curve on this surface. So although they didn't calculate them quite this way at the beginning of the century, that was information that was available. So what happened? Well, pretty much nothing for quite a long time, because we didn't have the computational capability to actually do much with them. On the left, though, from the 1950s to the 1980s, there was a lot of development in computer technology, as we all know, the hardware. But for us, one of the important developments that was also occurring was numerical techniques, numerical methods, and algorithms. And for nonlinear analysis, those are some of the key developments that were occurring during those decades. And that was really important for the kinds of things we wanted to do. On the other hand, in astrodynamics on the right, there was lots going on in developing capabilities for flight in the regimes that were fundamentally based on behaviors that we were more familiar with that could be broken down into pieces of the conic problem or the two-body problem. So some of these were obviously very successful. Not easy at all, but there was a lot that was going on in both directions. In the 1970s, they sort of converged. So in the 1970s, actually, we were looking at the Apollo program. And if I turn to applications in astrodynamics, actual flight, I can start off, first of all, with Apollo 18. So the Apollo program was very successful, going to the moon, all the trajectories that you use to get there. But Apollo 18 was proposed, and it was going to fly, and they were going to put astronauts on the backside of the moon. Now, the moon always keeps pretty much the same face pointed toward the Earth. So if the moon keeps the same face pointed toward the Earth, and you want to put astronauts on the backside, you don't want them out of contact. So you had to come up with a way that you could communicate with them. And there were various proposals for complicated formations of satellites that you could put in orbit around the Earth, and when they were out of contact with one, it would switch to the other, and so on. Then there was a proposal, which turned out to be from Breakwell and Farquhar, which was from my research group at Stanford before I joined them, that said, well, why don't we simplify this and just use a halo orbit, which mathematically we know exists, put it on the far side of the moon around one of those Lagrange points, and then you could communicate with the backside of the moon and you could communicate with the Earth simultaneously. It would take one vehicle and you could solve your problem and have 100% comlink. Calculating the orbit was non-trivial. You had to know it was there. It was predicted to be there in 1920 by Moulton. But Farquhar and Breakwell were able to actually do the computation and determine that you could actually do this. So this was a first glimpse of what might be possible. Unfortunately, Apollo 18 was canceled, so they never got to fly it. But Farquhar at that time was the head of flight dynamics at NASA Goddard. And never say die, that's his motto, I think. And so they came up with another mission that would do something similar. This is the IC3 mission, which launched in 1978. I don't have another graphic of it. So let me start out. Here's the sun. Here's the moon. Or, excuse me, that's the Earth. And the moon is in orbit around the Earth. But in this case, what they did, and Farquhar was part of this proposal, was to say, let me leave the Earth and let me go to a halo orbit out here about one of those Lagrange points, the one that's between the Earth and the moon. And they went out there, and it was very successful, and they got a lot of data out of the mission. And then what they found out was that this regime is very sensitive, it's chaotic. So they were expecting that they were going to have to spend a lot of propellant in order to keep it on orbit and all that kind of stuff. And it turned out they didn't, okay? Chaos can be used to your advantage. One little flick can keep you in orbit. You don't need to use a lot. So they had a ton left over, well, a ton in astrodynamics terms. Said, let's go to somewhere else. So they decided they would go to a comet Giacobini-Zinner, in 1985. And this is actually where I joined the story because I was now an assistant professor here when we took the spacecraft and moved it there. Now, the path to get it there was a little convoluted, okay? So this was something that you were not going to be able to accomplish. It also needed 5 passes by the moon and so on. But you had to use all those gravity fields. You had to put them all together in order to accomplish this. It was arduous. It took the NASA engineers about 7 months to calculate this with a team of people because they were just running like crazy. Some of them were integrating forward, some were integrating backwards, and they just hoped they connected. Okay, but eventually they got it. It was very successful. It flew by the comet. I was lucky enough to be, at Goddard when that occurred. All of this, and it was 12 seconds of wonderfulness. There were no cameras on it or anything, but they did get a lot of data in those 12 seconds. Okay, so it took a lot of time, but it was also, it sparked a lot of ideas because it said we could use all of this new information we had about multiple bodies and what they could do for us. And it opened up a whole world of possibilities. And this was, it first launched in '78, and it actually went by the comet in '85. So that was where they suddenly had great interest in doing all these unusual things. In that case, we also see something like this one, which is WIND. The WIND spacecraft is actually still out there and still flying. This one was also going to accomplish something interesting from the point of view, the sun is off to the left. Here is the Earth. This black circle is the lunar orbit. And all these colored things are the spacecraft orbit. It got to do a lot of different kinds of things to get out here and collect data out here. And so that was always important because this particular point, when you want to collect data from the sun, is beyond the bow shock of the Earth as it moves around the sun. So collecting data out there gave you a lot of good information. So, but wind was arduous to calculate, and again, you took a bunch of people just integrating and seeing what came out. There was no real understanding about what the possibilities, what the underlying dynamics was all about. This is SOHO. We're now in the mid-1990s. So this is 1994 for SOHO. That was where the Europeans joined the US in this particular mission. In this case, they wanted to do the same thing, and as a matter of fact, you may not be able to tell from this graphic, but they didn't feel very brave. So they used exactly the same trajectory that the first mission, IC3, had used in order to go out to this point in space. But it was successful. They had a little drama, but eventually it all worked out. Then we get other folks also interested in these things. On the top is Relic II. That was a proposal out of Russia, that they also wanted to start using some of these different kinds of scenarios. In this case, this is the Earth right here, and they want to go out to a point on the far side of the sun. So the sun's over to the left. Previous to that, they always used the libration point on the left, and now Relic II is looking at this point. If you want to study the sun, you go to this side. If you want to look out and study, like an astrophysical observatory, and study things away from the direction of the sun, you go out to this point. So Relic II was a Russian suggestion. Down here, this is MAP. This was a US mission. In both of these cases, what you're interested in doing is getting out there, but in both of the cases, they also had to add, these little guys here are called phasing orbits. These also add help from the moon. So also letting the moon help you get out there, and combining all those together uses less propellant. So there was an increasing interest in all of this. One of the problems, though, was that for the most part, the techniques to calculate these were burdensome, and you didn't have really a good idea of what was out there or what the path would be. So there was a lot of experimentation. And if you know a particular motion is there, you can search for it. But there's a lot of things you might not know. This one, for example, was one that finally we knew about because that type of behavior is fundamental to what all those previous missions were using. But there's a lot of others here. These are just some examples from some of my recent students of other possibilities. And if you don't know they're there, they're hard to find. Okay? You don't just magically say, oh, I'll try a few. You could experiment with initial conditions, I don't know, the rest of your career and not find them. So that was a problem. If I know the path's there, I can use traditional methodologies. If I don't know it's there, I'm going to have to do something else. So with missions getting increasingly challenging and more scenarios wanting to use them, it turned out that we needed to know more about the underlying structures. We needed more types and different types of numerical tools to accomplish it. And so we ran into a show-stopping scenario that demanded that we do something different. And that was the Genesis mission. Genesis was conceived at the end of the 1990s What they wanted to do was they wanted to send a spacecraft out to the point between the Earth and the Moon. What they wanted to do was open up, these are called collectors. There's material that streams off the sun, and they wanted to open up those collectors, grab a piece of the sun, close them up, and bring it back. That was the idea. But they couldn't, it was a Discovery class mission, which meant that they had a maximum amount of propellant they could use, and they could not get a trajectory that would accomplish the objective for the amount of propellant that they had available. So they were going to have to do something else. These are some of the types of ideas that were floated for the return path, and it turned out that it was just a really hard problem to do. My JPL collaborator called me up and said, we've got some contractors who are working on this, but nobody can get a solution that actually works. So let's go back and let's look at what we know, what we've learned over the last 15 years on what the actual structures are. And let's utilize those rather than the traditional approaches to these kinds of missions and see if we can get a solution. And actually, I remember very well the day he called me because it was a Thursday and he said, by the way, I need it by Monday. So one of my graduate students and myself eventually produced what looks like this. This is the Earth in the middle. The sun is out to the left. This is the lunar orbit. We move out from the Earth and get into this orbit around this Lagrange point, open up the collectors, spend some significant time out there, and then come back. But the dynamics tell you you cannot come right back to the Earth. So you cannot just come right back to the Earth. The only way to get back, the dynamical flow tells you that you need to come back from the other side. You need to go back to this Lagrange point, this region on the far side of the sun, and then try to come back into Earth. It is not a planar problem, it's a three-dimensional problem, so this was the out-of-plane behaviors. And so that was the challenge, and this is what we produced. Here, this entire thing took 8 meters per second total for the baseline design. This is the solution that we sent out, that left West Lafayette, and we sent it out to California along with 2 of my PhD students who they hired. And this is what came out from JPL after they doctored the picture, okay, and actually did a lot of the calculations. It actually turns out that there's 4 significant bodies involved in this problem: the spacecraft, the Earth, the sun, and it turned out the moon. So the moon, phasing of the moon was also important in order to get this back, because coming back to the Earth was also non-trivial. You had to come back. Remember, this is going to, actually it was going to come back to Utah, so it had to be snatched out of the sky. You didn't want it to burn up in re-entry, so it had to come in at a very particular angle. And interestingly, when you come back to Earth, there's also, at that time, there were also requirements that you couldn't have a trajectory, that this trajectory couldn't pass over any foreign countries. So it had to come in to Utah over the Pacific Ocean, all kinds of fun stuff. But it actually was very successful. And by the time that we were ready with the reference trajectory, there was no delta V in the baseline trajectory at all post-launch. So there was nothing you actually had to do. They did put a maneuver in at arrival just to be sure that they could control exactly where it arrived. But this was really a game-changing result from the point of view that it wasn't just the trajectory itself. It was that there were these other types of techniques, this understanding of the fundamental structures in this region of space that could be leveraged in order to produce what you want. We didn't calculate this by starting at the initial conditions and just guessing what the solution would be. We went to our understanding of all the structures out there and collected pieces and put them together. Now, we do that too when we have fundamental conic motions, but this was different for its time and sort of changed the way that we look at calculating these. So it was a really good mission to accomplish. One of the things we know about these kinds of structures is also that they create surfaces out there. So this was what we, of course, you know, these are NASA missions, so of course they didn't launch on time. And so we had to look at changing the launch date. And so these were the options, and you could just move from one to the other, and still they were on these surfaces. So it turned out to be a good way in order to start thinking about what the possibilities were. Since then, there's been a whole bunch of these. These are some of the missions that have been accomplished, not just in the US, but also Japan was associated with Geotel as one of some of the others. In more recent times, we see that there's a lot more out of ESA. Grail, of course, was part of this. And in just the last couple of years, the Chinese Chang 2 also used this methodology and these types of orbits in order to accomplish some specific objectives. So what's happening currently in the discipline associated with this is that we're trying to map what does all of these solutions look like in the solar system? What does it mean to be able to leverage all these gravity fields? And what are the options in addition to what we've recognized to be the case in these problems? We have to build up these dynamical structures. We have to understand the connections and all the linkages. And we need to build the tools in order to be able to access them on a design basis that the mission designers can actually use them. Then they also have to link to operational software, so that's something we've been looking at in recent times. Some of the latest missions that have used James Webb, actually it seems like I've been somehow connected to James Webb since 1985. It changes names, but it's the same thing. In retrospect, by now, in 2015, the trajectory, you don't have to read any of this, but the trajectory actually is pretty well known and we're pretty calm with working in that one. This was a more recent one. This was Artemis, which happened in 2010. This is the trajectory that goes from Earth, uses the moon in order to shift around, to also leverage the sun. The sun is way over here. This is not a trajectory that you would normally envision if you weren't working in our type of discipline. It was also the first one. Here is the moon. The Earth is to the left. When you got to the vicinity of the moon, these are the trajectories in the vicinity of the moon. The moon is in the center. These are these trajectories around empty points in space that then flip to the other side and eventually got into orbit around the moon. So from a trajectory perspective, in 2010 was the first time these kinds of trajectories were exploited in the Earth-Moon system. And so now all of a sudden we're thinking of doing more of that. Oh, this is my collaborator at NASA Goddard, Dave Folta, who has supported a lot of this stuff and was certainly part of the architect in operations for this Artemis. JPL computed the original trajectory, but Dave was responsible for the operations. And to be honest, I couldn't find another picture of him. So he's in the stereo lab at Goddard. This is Grail. Here is the Earth. Grail was trying to get to the moon. If you look at Grail, what you see is, oh, the path to the moon looks a lot different these days than it has in the days of Apollo. And it's not that the approach used by Apollo is not a good one. These are just other alternatives. So now we can leave Earth, do some other kinds of things, and come into the moon, leveraging the solar gravity as well. This is IBEX. This is just a mission that's already up there. One of the interesting things about IBEX was it was already flying and doing a trajectory that looked kind of different. And then they switched in flight to what they discovered was a trajectory that was resonant in the Earth-Moon space so that they could accomplish what they wanted to do and that it would be there for many decades. So where do I go from here? I'm looking at, Claude said it's this 7-year thing. I'm looking forward at learning more about all this. There is no solution to this problem in the traditional sense. So I need to look forward and figure out what don't we know that we have to do as we move forward. This is our neighborhood in the solar system world. This is where we live. Here's Earth. This is the moon. And the structures in the moon region, but this is also The sun is to the left, and so moving back and forth between our local neighborhood and our extended neighborhood is something that we want to do to accomplish objectives in the future. So I need to look at those kinds of things. We need to build up what the dynamical framework looks like. We need to be able to pick out how we're going to do this. We've had inquiries in the past of if we put an observatory over here, how are we going to move from regions near the moon over there? And so those are the kinds of things we need to be able to do. We need to understand all the structures in this different way of viewing the solar system and leverage them. Tons of possibilities. This was produced by one of my PhD students a couple of years ago. These are all trajectories in the Earth-Moon space. Okay? How do we use them? How can we leverage what we've got? Here are some more, just other examples. I mentioned IBEX a few minutes ago. This is that. This is TESS, an upcoming mission that's going to be coming out of Goddard. So there's so many possibilities. We need to actually put them all together, figure out how to get there, how to get home, how to get to other places. And so this becomes sort of a catalog, and a couple of us have been working in recent times with support from NASA headquarters to try to figure out how we can put a lot of this information and make it more accessible. That's just an example. I still work in exploration of all kinds of things, exploring other ways. Right now, low thrust is a big talk. And when I think about low thrust, I don't think about just calculating trajectories. This is low thrust from the Earth over to the moon. But when I think about it, what we're trying to think about is how we can leverage the new information, how we can use it. When we get to the vicinity of the moon, for example, this was a case where these are parts of halo orbits. So how can we leverage those to look at a solution which might hover underneath the moon, for example? So low thrust becomes more a problem of how do we take the structures we know and use low thrust in order to change or shift the structures. And so that's one of the things that we're looking at. Exoplanets has also loomed as something, looking for planets around other stars. So you're not going to be able to do that from Earth. So there's also formations to accomplish that. And some of those are some of the other concepts that we're interested in leveraging these new types of capabilities to accomplish. We use lots of computational tools. We use lots of visual tools. My poor graduate students pose for pictures all the time, okay? But these are just examples of the kinds of tools that we use to accomplish our objectives. This was also something having to do with material coming off Mars. So Loic made this particular image. It also says we're also looking at some of those things associated with natural objects. I would be remiss if I didn't also identify things that are important to me over the next 7 years in talking about educational innovation. I could have spent a whole hour talking about my thoughts on the curriculum and its developments and so on. But I do have some goals there as well. One of them is just in content delivery and taking all these tools we developed for this orbital space, all the visuals, and taking them and how can I harness that in order to give me better ways to deliver content in my classes, better ways for the students to work. So I just wanted to pull that in at the end. I also am a believer in developing capabilities within the students for modeling and simulation, which many organizations now, including NASA and some private companies, all have groups that do modeling and sim, talking about how to use simulation in order to do analyses. It's not just pretty pictures at the end of the day, and so I'm interested in furthering develop that. I've taught a couple of courses as an overload in the last few years doing modeling and sim. My first one was at the request of JSC, so because they have a large modeling and sim group. These are some of the images from that first course that we did. Giving the students an opportunity to see how to use this more effectively. At least a couple of students out of that group actually ended up working at one of those facilities. I have a current class I'm doing now. It's a little bit smaller, but we're trying to do something a little bit different that Cody over there is helping me with. Took a couple of images of those guys posing. But I think it's a direction that's going to be happening going forward. Even on board now, they're doing more simulations, and so that's something that we have to do in the future. So I wanted to just be sure to make that note that's also on my agenda over the next few years. To close, I would say I can do none of this without my graduate students. So both past and present, this is my current group, some of which are here. Some of them aren't smiling. Do you notice that? But I depend on them a lot. They have wonderful ideas, and they contribute significantly to what I do in the research arena, but also to the changes I'm trying to incorporate in some classes and things like that. So with that, I'm out of time. Do you guys have any questions? If not, the food's in the back, or, oh, it's gone. Lee?
Can you comment, what's the chance of a decent-sized asteroid will collide with Earth in the next 100 years?
Well, there's a lot of them on the radar. But that is something that is an issue, and particularly if we think that the sensitivity in the solar system is high. You know, the ones that we think are going to come close don't actually come as close as we plan. So I think that there's folks that are looking and keeping track of all of those. Yeah. Alina?
Okay, thank you so much for opening my eyes to what kind of neighborhood we live in.
Yes.
How difficult it is to get around. Do you think that at some point we will, what kind of weather, is there a dynamic factor in all of this? Is there a weather?
There is. There is. I mean, there's lots of things in that environment. You know, it's not as, you know, and actually there's a lot of satellites that they're trying to learn more about that.
And can we start cultivating the neighborhood?
I would like to do that. Yeah, so my view is that if we're going to move out from the Earth, okay, into our local neighborhood, our extended neighborhood, we have to know what the roads are, essentially. We have to know where we can go. We have to know how that we're going to get there. And so in my community, there's a group who are trying to assess that and trying to see what all the options are and stuff like that. Okay, and of course, especially if we want to build some kinds of facilities in low Earth orbit or beyond, okay, we have to understand better how we can access that space. And if we're going to have a permanent presence there, we need to know what all this is about. And right now, we know some things, but we could do more. We could have more information. I don't know, does that get anywhere close? There's a test.
I have a test question.
Oh, yes.
Which is better, Joy or Palmolive?
Palmolive? That's the wrong company. Dawn.
Which is a spacecraft.
Hey, you're quick.
Yeah.
I don't think there was a strong connection.
So I have a more serious question. Have you found that the visualization work that's advanced so dramatically that you've been leading, has that, in your mind, helped more people find this field accessible and become interested and more capable in doing the underlying modeling?
I certainly think the visuals help a lot in getting people interested in it. And, you know, we're looking at that not just for the pretty pictures, but to actually learn things. But sure, it gets a lot of people interested, it gets the students interested. But even more than that, I think the visualizations, for example, like in the classrooms, can make things accessible that they have a hard time understanding otherwise. So I would like to expand that use in the classroom. And if we can get to a point where they can interactively work with some of those things themselves, I think it'll have a great learning, it'll bump up the learning curve. Just from my experiences. Yes?
I'm a little curious about like computing time. So like we actually like calculate these orbits, or you know, here and the Earth, but the Moon. Like, what kind of like computing power does that actually take? So like a laptop, supercomputers, like.
Oh, I think these guys are all counting on their laptops, aren't you? But that's a serious problem on spacecraft because as soon as you leave the Earth vicinity, everything has to be calculated on board. And the computing capabilities on board are roughly, 10 years behind what we can do on Earth? And so that's advancing, but that's a issue. But we're so far ahead of where I was when I started, so this is all, gravy as far as I'm concerned. Yeah. It's advancing rapidly, however. But you have to be, judicious. So you just can't say, I'm just going to calculate it all. And so one of the things that I think some of my guys are trying to do is trying to say, okay, how can we be smarter and identify enough with crude information to help us know where to do the more detailed computing. Okay. And some of that we might be able to learn visually, but not all. Okay? There's more, there's still more in orbits to learn. I will say once when I was, probably just a new associate professor, I had a visit from an unnamed university aerospace engineering head who was checking to see if, isn't everything in orbits already known so I can just eliminate that from our curriculum? And of course I said no. So there's still a lot of unknown things and there's still a lot that we can learn and there's still a lot of opportunities. Anybody else? So John, how was it? Thank you all very much.